We are Team STEM to STEM, and we have created a sensing tourniquet for emergency medicine to stem the flow of bleeding. Our project design is a pressure sensing tourniquet intended for emergency military application within the context of bleeding control. In assessing the needs of a combat tourniquet, we looked at the common complications of tourniquet use. Typically, the major complications involved are ischemia and tissue necrosis, reflow injury, and nerve damage. Unfortunately, ischemia and reflow injury are inherent with arterial occlusion and the successful use of a tourniquet. To this end, we aim to limit nerve damage associated with tourniquet usage, and most studies suggest that decreasing the amount of pressure will help to mitigate subsequent nerve damage. In fact, in a surgical setting, clinicians measure limb occlusion pressure prior to application of a pneumatic tourniquet in an effort to minimize the amount of pressure necessary to effectively occlude arterial flow and therefore reduce nerve damage. This type of device does not exist in the form of a mobile field tourniquet, and it's often reported that tourniquets applied in the field are generally cranked as much as possible. This means patients that need tourniquets applied in emergency settings are at serious risk for excessive nerve damage. In a civilian setting, extremity hemorrhage accounts for 0.02% of traumatic deaths. However, in a military context, extremity hemorrhage accounts for around 9% of total deaths. This makes soldiers the greatest at-risk population for tourniquet-associated nerve damage. Therefore, our device aims to attenuate nerve damage for military personnel as a result of excessive pressure from tourniquet use in an emergency setting. Our prototype features a three-part, 3D printed housing that fits onto a mechanical advantage tourniquet. Within the housing, we're using a backlit color display LCD powered by an Arduino Nano and a 9-volt battery. The system can be turned on and off with a latch switch designed to lay flush with the device surface when turned on to prevent accidentally switching it off. To sense pressure, we have incorporated 3 force-sensitive resistors that we've embedded in silicone to ensure placement within the tourniquet. Initial calibration of the resistors began by converting data included in the product insert from grams and resistance change to pressure and bit voltages, so the Arduino Nano could translate input data into millimeters of mercury. However, once we embedded the resistors in silicone, it reduced their sensitivity, and we had to develop an adjustment multiplier by placing our sensors under a pneumatic pressure cuff, and then comparing the measurements of the cuff to our digital readouts. We did this by incrementally increasing the pressure of the cuff and recording both pressures, before generating a curve to recalibrate the sensors within the silicone. This eventually gave us digital readouts within 15 millimeters of mercury of the pressure cuff, which we deemed satisfactory. Currently, we're also using an automated timer to help alert clinicians at a treatment center the exact time the tourniquet has been applying pressure. In this case, 50 millimeters of mercury initiates the timer. We're also using 250 millimeters of mercury as an example limb occlusion pressure threshold based on a healthy systolic blood pressure of 120 and an additional published safety margin of 100 for a healthy adult male, plus another 30 to account for the potential 15 variability within our current prototype. To validate the device, we used Doppler ultrasound to visualize the pulse of the radial artery in the wrist. We then applied the tourniquet to the lower arm and began slowly increasing the pressure of the device until the backlit LCD turned green, indicating that we'd reached the earlier proposed threshold of 250 millimeters of mercury. With that amount of pressure applied, we were able to completely occlude arterial flow downstream of the tourniquet without having to crank the tourniquet until we couldn't crank it anymore. Our device shows proof of concept of taking a well-established clinical methodology of minimizing tourniquet pressure into the field of emergency medicine. While it's clear that there are many steps to take before taking this device to the market, we think it provides clear evidence that a device cognizant of an individual's limb occlusion pressure can be used to help mitigate tourniquet-associated nerve damage.